Today in class we introduced vectors. Let's say that I asked you to walk for 50 feet. Is that the same as if I asked you to walk 50 feet east? And if not, what's the difference? A vector is a geometric shape that has length, otherwise known as magnitude, and direction. The difference between the two questions of walking 50 feet and walking 50 feet east, they both have a distance, but only one has a direction. And the one that has a distance and direction, or length and direction, is a vector. In math, we represent a vector using an arrow. Now this looks similar to a ray. It's not. A ray goes on forever in one direction. A vector has a starting point and a stopping point, and we're going to talk more about that in just a minute. We can represent a vector using an arrow, but we also need to know how to name a vector. First, if I don't know any points on my vector, I just simply use a lowercase letter. Then we use the vector symbol. It's very, very close to that ray symbol again, but just not quite. Let's say you went 30 miles west. On a map, west goes to the left, so that's why this vector is pointing left. And then I did it again. We would call that 2v. I have double the vector that I had before. And what if I did it one more time? Yep, that would be, let me get my pen here, that would be 3v. Make sure to use your vector symbol when you're talking about your vector. Let's look at a vector on a grid. The beginning point is called the initial point, and the ending point is called the terminal point, and this terminal point is what the arrow is pointing to. This vector has a magnitude and a direction. Let's look at how to find both. The magnitude of a vector is its length. So I can use either the distance formula or Pythagorean theorem to find it. This time, I'm just because that's what I wanted to do, I'm going to use Pythagorean theorem. So I have leg lengths of 6 and 3. So I know that 6 squared plus 3 squared is equal to v squared. That gives me 36 plus 9. Which means that 45 is equal to v squared. So I need to bring up the calculator and I'm going to find the square root of 45. Rounding to the nearest hundredth, that gives me 6.71. So I'm going to write that v is approximately 6.71 units. Now this is its magnitude, right? I actually write that with double brackets, and I say that the magnitude of vector v is 6.71 units. Let's skip that. If I wanted to find the magnitude of this vector again, I could use the endpoints. I have -8, 4, and I have 1, -2. I can use distance formula, which would give me -8 minus 1 squared, and 4 minus -2 all squared. That's going to give me the square root of 81 plus 36, which gives me a total of 117. And so if I want to find the square root of 117, rounding to the nearest hundredth, I get 10.82. 10.82 units. And again, the symbol for magnitude, I'm finding the magnitude of vector u is about 10.82 units. The direction on a vector is almost like a point, or at least it looks almost like a point on a coordinate plane. It's not exactly like one though, because we're not going for exact placement like a point. we're looking for displacement, which means change in direction. Notice that we use a different set of parentheses, right? And I want to look for the change in x and the change in y. Here I have vector AB. This is one other way to name a vector. I always want to put the initial point first and the terminal point second, along with the correct vector symbol. The displacement for this vector, again, the first number is going to be the change in y. I went from -5 to +5. That's a change of 10. For my y values, I went from 2 all the way up to 7. That's a change of +5. So this is how I would represent the displacement of my vector. Two vectors are equivalent if they have the same displacement. They're going to have the same magnitude and they're going in the same direction, and that's all it takes for vectors to be considered equivalent. So notice I have vector AB, I have vector CD. Both displacements are -7, -5. We went -7 in the x direction and -5 in the y direction. So these two vectors are considered equivalent. And finally, since displacement is the change in position, there are certain times when we can actually combine two vectors. Let's look at one of those now. An ant walks forward 10 steps, then reverses direction and walks 7 steps the other way. The picture of that is going to look like this, showing that I went 10 steps in one direction, and then from that same place, from that same ending place, now I went 7 steps back. What are the total number of steps that ant walked? Well, if I add the two together, 10 plus 7, there are 17 steps that ant took. However, the displacement, right, is different. My initial point is here, and my final terminal point is here. The difference between the two is only 3. So where the total was 17, the displacement was only 3. There is a difference. Let's say that Anna is walking to her friend's house and she walks 8 blocks north, then turns and walks 6 blocks directly east. If I wanted to draw a picture of that, it would look like this. How far did she walk? How many blocks did she walk total? She went 14 blocks total. However, the displacement is different. Her displacement goes from the initial point directly to my final terminal point. Pretend like that line is straight. Since this is north and east, I can guarantee that that is a 90-degree angle, and I can use Pythagorean theorem to solve. If I do that, I'm going to find that her displacement was only 10 blocks. Sometimes you'll hear that stated as the crow flies. Displacement is the distance as the crow flies. Just a little bit of review. Naming a vector. If you don't know any points on the vector, you can just use a small letter. If I do have points on the vector, I use the initial and terminal points and the same symbol. To represent a vector in component form, right, again, this is the displacement vector, I can say the change in x and the change in y. And magnitude, of course, was our length or distance. Make sure to write down any questions so you don't forget to ask me tomorrow. And your assignment is workbook pages 471 and 472. Have a great day.